Hi everyone. So this lecture is on the series of lectures on operational amplifier circuits. Now I said we will discuss about the design of CMOS operational amplifiers very soon. But before we discuss that, I thought there is one other interesting topic in op-amp circuits which I thought is it's the right time to discuss now. Now the topic that we will be discussing today in this lecture is the switched capacitor circuits. Now, the switched capacitor circuits were popularized around, in fact, they reached their peak in 1980s and 1990s as an alternative for continuous time analog filters. In fact, DSP was seeing a huge revolution in 60s, 70s, and 80s. So this was seen, switched capacitor circuits were seen as a promising candidate for signal processing. But we will very briefly, keeping that in mind, I'll very briefly discuss in today's lecture, just introduce you to the idea of switched capacitor circuits. What is a switched capacitor circuit? Now, quickly, before we discuss that, I'll discuss some basics and then we'll start looking at the idea behind switched capacitor circuits. So shown here is a resistor to which we have applied a voltage. So we know from Ohm's law, V equals IR. So if the current through this resistor is made to go to zero, then the voltage will also become zero instantaneously. So such an element, so I've shown here in the second picture, where we see that a current is being injected into the resistor, and if the current goes to zero, then the voltage across the resistor will also go to zero. Such an element is what this two-terminal element is what we call a memoryless element. It doesn't store or have any memory of what was the voltage or current that was stored previously. On the other hand, if you consider a capacitor and a current that is charging a capacitor, we know a capacitor acts like an integrator. So the current voltage at any time instant across the capacitor will be whatever be the, for example, if a current is charging it, the incremental voltage due to this current that's charging it at that time instant, plus the initial or the previous voltage stored across the capacitor. So a capacitor has a tendency to accumulate voltage. So it acts like an integrator. So an accumulator or an integrator stores the previous voltages. The operation of accumulation is better illustrated if you assume a switching operation. So what I'm going to do is that I'm just going to introduce a switch between the current source and the capacitor. And this switch will be controlled by a clock signal which will be on for t by 2 seconds and off for t by 2 seconds, where t is the clock period, which is given by 1 by f clock. F clock is the frequency of the clock period, of the clock signal. Now, when the clock is on, the current I will charge the capacitor and it's on for t by 2 seconds. So the voltage stored across the capacitor at the end of t by 2 seconds is going to be I upon C, it's a constant current. So I upon C into t by 2. So the voltage, I can write it as I by 2C into T. So this will be the voltage across the capacitor at the end of T by 2. Now, between T by 2 and T, there is no current that's flowing through the capacitor. So what will happen at that point, the capacitor will retain its memory. So will retain its voltage because it's a circuit element with memory. So the voltage will remain constant. So this is how the voltage will look like. It looks like a staircase function. Again, for t seconds to 3t by 2 seconds, you 3 t seconds to 3t by 2, you will again be charging it and the voltage will be held constant from 3t by 2 to t. So at the end of the second cycle, the voltage across the capacitor, it's going to be I by 2c into t. So this is the charge or voltage that's transferred in the second cycle, plus the voltage in the first cycle, which will be I by 2c into t. So it will be 2 times I by 2c into t. So at the end of nth cycle or ith cycle, it's going to be I into t by 2c into t. So at every cycle, you're going to add a charge or voltage of value I by 2c into t. So it's accumulating it. Now, if I want to convert, if I have to convert a capacitor which has the tendency to accumulate voltages, if I want to convert it into a resistor, then I need to introduce some kind of a reset mechanism. So here if you see, the voltage is getting stored when there is no current that's being injected into the capacitor. The voltage is remaining constant. It's holding its previous value. That's where the difference between a capacitor and a resistor arises. A resistor is a memoryless element. When there is no input, there will be when there is no current, the voltage developed across it will also be zero. But a capacitor will retain its voltage, will retain its previous value. So if I can somehow eliminate that retention ability, so if I can somehow eliminate that accumulating ability, then I can try to mimic the behavior of a resistor. So that's what I've shown here. I have, instead of voltage source, I'm showing it using a current source. I have two switches shown here. One switch is controlled by a clock signal. The other switch is controlled by clock bar, the inversion of the clock signal. That's the signal that controls the other switch. During one cycle, when the switch is on, this capacitor will be charged to a voltage of Vx. So I've shown the waveform here. So if I assume the switch has a finite resistance, then the circuit will reduce to something like this. In the positive half cycle, your capacitor will be charged to a voltage Vx, and in negative half cycle, this switch will turn on and it will discharge the capacitor. Okay, so in the positive half cycle, it charges, and negative half cycle, it is discharged. Now we'll look at the current waveform and see what kind of a current is actually being drawn from the input voltage source. So in the positive half cycle, you can just represent the switch by a resistance of value RSW. So what happens is the voltage across the capacitor goes from 0 initially to Vx. And the current through the capacitor, or current drawn from the input, starts from a peak value of Vx upon RSW. It starts from a peak value of Vx by RSW, and then it goes to 0 at t by 2 seconds. Right? Within one half cycle, it goes to 0. Right? So that's the point where charging has fully happened. Once the capacitor is charged, then no current is transferred from the input. No more charge is transferred. Hence, no current is transferred from the input. So the current goes to 0. So this is how the current waveform will look like. Of course, if you know the voltage waveform, you just have to differentiate the voltage waveform, you get the current waveform. So voltage waveform looks like this. You differentiate it, you will get the current waveform. In the next half cycle, the capacitor is discharged by the resistance, the switch resistance RSW. So initially the voltage across it will be Vx by RSW, and eventually it will go to 0 from t by 2 to t seconds. So whatever charge the capacitor was charged to, it will be fully discharged by the end of the first half cycle, the first full cycle. Okay. Now, if you plot the current that's drawn from the input is in connection with the capacitor only during the positive half cycles. From 0 to t by 2 seconds, the input is connected to the capacitor. So during that cycle, it's going to draw out, so this is the circuit. It's going to draw out a current waveform which looks something like this. What do you think will be the current waveform if the switch resistance was 0? If the switch resistance was 0, how will the current waveforms look? The capacitor is charged suddenly, instantaneously. It will look like an impulse, right? And what will be the weight of the impulse? Equal to the area under this graph. It will be the charge, the entire charge, which will be C times Vx. Okay, so the waveform for an ideal switch, it's going to look like this. It will be an impulse at 0 t seconds. It's going to look like this. Okay, or for a realistic switch resistance, for a practical switch resistance, the waveform is going to look more like this. So Vx by RSW, and it will discharge with the time constant given by RSW into C. Now the area under this graph, the current waveform, is simply its current. If you integrate current, you get charge. It's the charge that will simply be equal to C times Vx. Now the current drawn from this voltage source now in this new circuit is a transient current. It peaks, goes down to 0, and another cycle it peaks, then goes down to 0, and so on. Okay, the current peaks, goes down to zero. This is the current waveform that's drawn. Now, when you compute the average current that's being drawn out of this, you'll have to compute the average of this waveform. That is simply 1 by t integral of the current in one cycle. Now, this integral of the current in one cycle is nothing but the charge transferred. That will be C into Vx upon t. Now, if you see the average current that's being drawn by this capacitor is actually finite. So, for example, if I were to charge a capacitor directly using a voltage source Vx, there is no current drawn in the steady state. Initially, maybe you will draw some current, but in the steady state, you will not be drawing any current at all. Okay? Or if, let's say, there was no discharging path, what do you think will be the current waveform? If I ask you to plot the current waveform, and let's assume there was no discharging path, how will the current waveforms look like? The first cycle, when you're charging it, it's going to go to a peak and then come down to zero. What will be the waveform in the second cycle? I mean, from 0 to t at t seconds, what will be the current waveform? Remember, the capacitor is already charged to Vx. There is no discharging now. It will stay at zero. The current will actually stay at zero. Okay, so it's not a resistive behavior. The current will stay at zero. But now, the act of introducing this additional switch discharges the capacitor. So the capacitor keeps consuming current from the DC voltage source even in the steady state. Now, only a resistor will drain out a constant current even in the steady state. So that's how we are mimicking the effect of a resistor. So the average current drawn, if you see here, is proportional to the voltage. And the proportionality constant here, 1 by R, I equals V by R, is the Ohm's law. From that we can see it emulates a resistance, equivalent resistance between the terminal Vx and ground. And the value of the resistance is given by 1 by C into F clock. Okay, that's the value of the equivalent resistance that's emulated by this capacitive circuit. Okay, so this circuit is what we call a switched capacitor circuit. Using a capacitor and some switches, some arrangement of switches, we are able to emulate a resistive behavior. And the value of the resistance is given by 1 by F clock times C. So it depends upon the time period and also on the capacitance value. Now we'll look at what we have seen now is a grounded resistor. So one terminal is not accessible for the resistor. The other terminal is accessible. So we saw how to emulate a resistance for a circuit for a grounded resistor. What if I want resistance between two terminals? Let's assume node X and Y as shown here. Then if I apply a voltage Vx and Vy here, the current drawn is simply given by Vx minus Vy by R. So current should be proportional to the difference in voltages between the two terminals. Now let's look at this arrangement here. I have switch between the two terminals, and one of the switches is controlled by clock and the other switch is controlled by clock bar, invert of the clock signal. And we will see how the current, what will be the profile of current that's being drawn from the node terminal Vx and the current that's injected into the node terminal Vy. Because remember, we have to emulate a resistor. Okay, so first let's look at the charging cycle. In the first half cycle, this switch S is on and it will charge the capacitor. So the circuit will look something like this. So let's assume the switch resistance is so small that you're able to instantly charge the capacitor within that half cycle. So what will be the voltage across the capacitor at the end of the first half cycle? At the end of t by 2 seconds, the voltage across the capacitor will be Vx. Now, so the voltage across the capacitor is Vx. At the next half cycle, the second half of the cycle, from t by 2 seconds to t seconds, the switch S bar is closed and the circuit will look something like this. So you'll have Vy, the capacitor is already charged to Vx volts, and now you are charging through the switch. Now, what is the total charge transferred from the voltage to the capacitor? Remember, if the capacitor had no charge across it, then the total charge transferred will be C into Vy. But now the capacitor already has a charge of CVx. So you have to only transfer some excess charge. So the excess charge will be C this charge CVy minus CVx. So that will be C into Vy minus Vx. So that's the charge you are going to transmit from voltage Vy to the capacitor. So at the end of first half cycle, at the end of t seconds, what will be the voltage across the capacitor? At t by 2 it is Vx, at t it is Vy. The voltage across the capacitor will be Vy. So that's what the circuit will look like in the next half cycle. The next half cycle, you will start with a voltage of Vy across the capacitor, and then you will charge it to Vx through this voltage source Vx. Now, what is the charge that's being delivered from Vx to the capacitor? Capacitor already has a charge of C into Vy, and Vx has to, you have to deliver a charge, an excess charge of value C into Vx minus Vy. It already has C into Vy, so you'll have to deliver an excess charge of C into Vx minus Vy. So when you add this to C into Vy, you get CVx. Right? You're supposed to charge it to Vx in this half cycle. And the process continues. So now if you look at the input has actually is delivering in the steady state. If you see, every cycle the input will deliver a charge of C into Vx minus Vy. Every cycle the input will deliver a charge of C into Vx minus Vy. Now if you look at this Vy, the terminal Vy, every cycle it is delivering a charge of C into Vy minus Vx. Okay, the direction of flow of current will be in this from Vy to the capacitor. Or I can simply invert the polarity and say that the capacitor is delivering a charge of value C into Vx minus Vy to the node Vy. So now if you see here, at the beginning of the half cycle, you are extracting a charge of value C into Vx minus Vy from Vx. At the end of the cycle, you are delivering the same charge back to the node Vy. So charge delivered is same as charge drawn from the node Vx is same as the charge delivered to the node Vy. So Kirchhoff's current law is valid there. And this, now if I plot the current waveform drawn at the input terminal, at the node Vx, if you draw the current waveform, it will look something like this. Right? So if the peak current is going to be Vx minus Vy divided by RSW, that's RSW is a switch resistance, then it will decay down to 0 within t by 2 seconds. And the same process continues. In the next half cycle, there is no current drawn from Vx. In the next half cycle, you are going to draw current from Vx. If the switch resistance was 0, I mean the area under this graph, what will be the area under this graph? That will simply be C into Vx minus Vy. That's the area under that graph. Now, what do you think? How do you think will be the graph of the current drawn or injected into Vy look like? What is the difference? What do you think is different? This is the current drawn from Vx, then I'll call it Ix, drawn from Vx. If you are to plot the current drawn from Vy, can I say simply, it's going to, because at this node terminal, you will inject this current. So the current will be just shifted by t by 2 seconds. The current waveform will just be shifted by t by 2 seconds. That's it. Now, if I look at the current drawn from the input terminal Vx to Vy, we are looking at the average behavior. In the steady state, what is the average current drawn from Vx and delivered to Vy? That will be the average value of this current. That is simply the charge stored per cycle, which will be C into Vx minus Vy divided by T. That's your average current drawn from the input. And this is the same average current which is delivered to the node terminal Vy. Right? So that's the same current that's delivered from node X to node Y. So now if I draw the average current drawn, that will be C by T into Vx minus Vy. Again, if you see, the average current is proportional to the voltage difference. So it's behaving like a resistor. And the value of the equivalent resistance is again C by 1 by T by C, 1 by C by T, which is T by C, or 1 by C into F clock. So we are able to emulate a floating resistance using a capacitor under switch arrangements. Okay. Yes. So one of you are asking, won't the current drawn from Vy be negative? So remember, I told two things. One, That is current drawn from Vx and current drawn from Vy, or current injected into Vy. So current injected by Vy, current drawn from Vy will be negative, but current injected into Vy from the capacitor will be positive. If you look at the direction, I'm look at the direction, I'm showing from capacitor into Vy. Okay. Now, when I began the lecture, I said one of the reasons why switched capacitor circuits gained prominence was discrete time signal processing, and the other advantage is process invariance as far as time constants are concerned. So, what do I mean by that? I'll explain it now. Now, these are two popular op-amp applications. One is an integrator. This is an inverting integrator, and this one here is an inverting amplifier. Okay, an integrator and an amplifier. So now, if let's say let's first look at the amplifier, the integrating amplifier, the inverting amplifier. Now, practical op amps, if you recall from your previous semester's course on, at least we just introduced to the idea of operational transconductance amplifiers, we said most op amps are operational transconductance amplifiers, meaning their output resistance will be very high. Now, if you see op amp, when it's trying to charge the output node, it has to charge its own output resistance, or it will be loaded by its own output resistance, and there is also load from the resistors R1 and R2. So the resistance R1 and R2, there is some path for current through that as well. So this is called resistive loading. So if you have a resistor, then that will start loading your op amp. For an ideal operational amplifier, the output resistance is 0. It's an ideal voltage output. But for a practical CMOS amplifiers, most of them are operational transconductance amplifiers, this circuit will be a problem. If you try to implement this op amp using an OTA, very high gain OTA, operational transconductance amplifier, the resistor will start loading it. So we may have to do some modifications to the op amp. We may have to add a very low impedance stage at the output. If you want to use it as an inverting amplifier with a resistive load, in the feedback path, you have to go for that. Now we will see in a few moments that if I realize this circuit using a switched capacitor circuit, then I will not need, there are no such requirements on the op amp. So now we'll see if there is a way of building an inverting or a non-inverting amplifier using a switched capacitor circuit. So let's look at a circuit which is shown here. The switch arrangements look a little bit complicated. I probably made it a little bit complicated, but I'll probably simplify this. So we just have one capacitor. Yeah, so we have one capacitor that looks something. So we have a switch here, a capacitor, and a switch here. This is sufficient. And I have a capacitor in the feedback path. So let's call this C2 and C1, and that has a discharge path through another switch. Now, the operation of these two circuits are very similar. You will get same results. So I think I'll analyze this circuit itself and show you what will be the average value at the output for a DC input. I've applied an input of value Vx. We'll see what is the output voltage. Now these two switches, this switch and this switch are controlled by a signal S, clock signal. The switch here and this switch are controlled by clock bar, the invert of the clock signal. And this switch across the capacitor C2, it's mainly for discharging the capacitor, because if you don't discharge capacitor, it has a tendency to store voltages. So we need to emulate resistor behavior. So we need to discharge it every cycle. So that's why you have a switch to discharge it. This switch is also controlled by the clock signal. So if you recall, our clock signal is on for T/2 seconds, off for T/2 seconds. Clock bar is the inverted version of this. So you'll have 0 for T/2 seconds and 1 for the other T/2 seconds. So in the positive half cycle, the circuit reduces to something like this. This switch will be open, S bar is open. So your capacitor will be fully charged to the input voltage Vx. Your op amp is in a unity follower mode. So what will be the output voltage? This node is at ground. So what will be the output voltage? It's in follower mode. Output will follow the input, so it will be 0. Okay, output will be at 0 volts. Now in the other half cycle, in the next half cycle, your capacitor is now charged to Vx volts, but this switch closes, this switch closes. These two switches, switch here and the switch here will close. The other two switches will open. So input is now disconnected from the capacitor. So this is how the circuit will look like. Your capacitor will be connected to Vx this way. Now, your op amp, what kind of feedback your op amp is in now? What kind of a feedback is this? Is it negative or positive feedback? It's in negative feedback, right? Because your input is fed back through capacitors at the negative terminal. It's in negative feedback. If the feedback is negative, what will be this voltage across or at this node? It's a feed, I assume it's an ideal op amp. 0, right? That node voltage will be 0. But that capacitor, previously, what was that node voltage? Instantly, let's say negative feedback hasn't kicked in yet. You have stored a voltage of Vx across this. So if this node is at 0 volts, this node will be at minus Vx, right? So roughly something like that. You have stored your capacitor. You have charged your capacitor to voltage Vx. But now op amp's feedback is forcing this node here to go to 0 volts. So what will happen to the charge in this capacitance C1? It has to go to 0, right? Op amp is trying to make it go to 0. So where will that charge go to? That charge has only one path, right? It has to go through C2. Okay, so now just quickly, if you see that you have charged this plate, the capacitor, this plate of the capacitor to a negative voltage, and this plate here to a positive charge. The potential at this plate is Vx volts lower than this. So that negative charge will be pushed to this other plate of the capacitor. So this will be this capacitor, the one plate of the capacitor will be negatively charged. To maintain charge neutrality, your op amp will inject a charge which is exactly equal in polarity. Okay, the charge that the op amp will inject will be equal to C1 into Vx. That charge will come from the op amp. In fact, when I say charge, it comes in the form of current. Okay, for a short duration, if you integrate it, you will get the charge. So the op amp will deliver a charge of value plus C1x to the other plate. And this charge, the negative charge present on this plate of the capacitance will go to C2. Okay, and the positive charge will be grounded, discharged to the ground. It will go through the ground. So this capacitor C1 now has 0 charge across it. Okay, op amp's feedback action is forcing this. The charge is coming through the op amp through capacitor C2 and so on. Okay, you can look at the current direction. It will look like this. This will be you need to have a return path. So the ground of the op amp will serve as the return path. So op amp will have its own ground, so that will serve as the return path. So this will be the total path for the current. So now you know the charge across the capacitor C2 is C1 times Vx. So what is the voltage across C2? Charge divided by the capacitance. So it will be C1 by C2 into Vx. So your output voltage is positive. Okay, so divided by C2. So it will be C1 Vx by C2. So this will be the voltage across the capacitor C2. So what kind of an amplifier is this? Inverting or a non-inverting? It's a non-inverting amplifier, right? Its output is positive and it's non-inverting. Now if you see, it gives you the same benefit that your gain is ratio of 2 capacitors instead of 2 resistors. So if your capacitor values change and both the capacitor values change in the same direction, which is something that you can expect in an integrated circuit, when you place 2 capacitors very close by, they both will have similar variations. Okay, so for similar process variations. So if both the capacitors change by the same amount, the gain will also remain process independent. Okay, but now if you see, there is no resistive loading in the circuit. I've completely removed resistive loading. You're either seeing in the unity follower mode or you're in a capacitive load. The load is a capacitive load. What's the problem with the resistive loading? Let's say I had a resistive load. What is the problem with that? What reduces if I have a resistive load? The DC gain will reduce, right? The resistor will start loading the output, the op amp's output, the amplifier's output, and that will decrease your DC gain. That problem, the DC gain problem, doesn't exist here. Okay, but remember, your input is not always connected to the capacitor. Your input is connected only for half cycle, and that you then dump in the next half cycle, you dump it at the output of the capacitor. Okay, so and this circuit behaves as an amplifier on an average. This is more like an average behavior. We didn't look at the transient waveforms of C2. We just directly calculated the total charge transferred in the cycle and just wrote this value. Okay, so that's why in these switched capacitor circuits, for the circuits to work very well, the input should look nearly constant in the clock interval. So which means the input signal frequency, I'll call it F sig as the input signal frequency, should be much lower than the clock frequency. Right? So if you have an input which is varying very slowly, then even though your switch is not open for some time because the input is changing so slowly, it will not be a problem. Okay, we'll talk about this in more detail when we explicitly talk about switched capacitor circuits. But right now, I just wanted to introduce the idea of switched capacitor circuits before we discuss the design of op amps. The next circuit we will look at is an integrator. An integrator, the transfer function of an integrator is minus 1 by SRC. Okay. Now, if you see the time constant of this integrator is given by RC, and it depends upon a product of resistor and capacitor. Now, resistors and capacitors are independent elements. So I can have resistor varying in two different directions. So the variations in both in the time constant will be the sum of variations in resistor and capacitor. So the time constant can change if your resistor and capacitor process corners change. That's the problem with this. So if you want to build a filter, generally if you want to realize filters, you can realize filters using integrators and gain elements. And if the time constant of an integrator keeps changing, then the filter transfer characteristics will also keep changing. That's the problem. So that's the problem with a conventional RC integrator, is that the problem here is that the time constant is prone to changes, process variations. Now, if I realize this resistor using a switched capacitor, instead of R, it's going to be, let's assume some other, let's this resistor capacitance be C1. The resistor is realized using a switched capacitor of value C2. The value of the resistance is going to be 1 by C into F clock. C2 into F clock times C1. Now, what happened to your time constant? Your time constant is given by 1 by F clock into C1 by C2. Now, if you notice here, the gain or the time constant, the time constant of this integrator is a ratio of two capacitors. It's a very interesting result. It tells you it's the ratio of two capacitors, which means if you fabricate both the capacitors close by, both of them will have similar process variations. You have now built a circuit, an integrator, whose time constant is constant, it's process independent. That's one very attractive feature of a switched capacitor circuit. So they were used in realizing filters, analog filters. But the problem with this circuit, I'll probably finish discussing this and then talk about this in detail. So we'll now look at a switched capacitor based integrator. So let's look at this circuit first. So I've just replaced this resistor. If you recall, a floating resistor can be replaced by a circuit that looks like this, right? Two switches and a capacitor controlled by opposing or non-overlapping clocks. Okay, into inverted or non-overlapping clocks. In the positive half cycle, you will be charging this capacitor to voltage of Vx, and your capacitance C2 will be in feedback. Your op amp will be in feedback. Okay, there are some small problems with the circuit, but right now we'll ignore that. We're not concerned with the more detailed versions of the circuit. I just want to illustrate the fundamental operation of it. So if the switch is open, you will charge the capacitor to a C1 volts. What will happen in the other half cycle? In the other half cycle, you will end up with a circuit like this. So you will have the capacitor C1 now charged to Vx volts and C2 this way. So now there is negative feedback. So op amp will try to force this node to 0 volts. Then what will happen? You had positive charge on this plate. This positive charge has to escape to this plate. So this plate will be positively charged. The positive charge on this plate goes to this plate, right? The voltage across the, what should be the voltage across the capacitor C1 eventually? The negative feedback will force it to 0, right? It is going to force it to 0. So which means it has to lose all its charge. The negative charge will go to the ground here, and the positive charge will go to this plate here, and op amp will supply the negative charge to the other plate. So that will be, and the value of this charge, the charge on the positive and negative plates are the same, will be C1 times Vx. This here is the charge that is transferred from C1 to C2. That divided by C1 times Vx divided by C2 is the voltage across the capacitor. Okay, so remember this voltage is in this way. The polarity of this voltage is this way. So C1 by C2 into Vx, I have shown the polarity. This is positive and this is negative. So what will be V naught in this cycle? This node is at 0. So V naught will be minus of C1 by C2 into Vx. Okay, it will be minus of, because if you see this plate is at a higher potential compared to this plate. The output plate is at a lower potential. If the voltage across the capacitor is C1 by C2 into Vx, and I know this node voltage is 0, then this node voltage has to be minus of C1 by C2 into Vx. Okay, now what will happen in the next cycle? In the next cycle, this capacitor is now discharged. The capacitor volt C1 has 0 charge. Again, you will charge the capacitance to Vx. You will charge it to Vx. And what will be the voltage across this in the next cycle? Remember, this capacitor C2 is not discharged now. Previously, it was getting discharged in the previous circuit. It's not discharged. Now you will again add the same charge. So it will be minus of 2 times C1 by C2 into Vx. So at the end of I cycles, it's going to be minus of I into C1 by C2 into Vx. So we have an integrator. Okay. So the integrator, if you see the integrating, I mean, this is a discrete time integrator. So you don't see the time constant. But what you see here, the integrating time constant, if I can calculate it and show that it is independent of process variations. It will be a ratio of two capacitors. That's why we get that advantage. So this I have shown here another version of, I have just analyzed this circuit in the non-inverting amplifier. The same circuit, if you just remove this capacitor, remove the switch S, because this switch S was discharging this capacitor. Every cycle, this capacitor was dumping some charge, right? And this switch was discharging it, but now I've removed the charge. So every cycle, if you keep dumping the charge, this capacitor C2 will keep on taking the charge again and again, every cycle. So it will keep accumulating it. So you have, this is a non-inverting integrator. So you can show very easily, the positive half cycle, you will charge this capacitor to Vx. Okay, so this plate will be at negative voltage. And when you connect the other way, when you connect this switch here and this switch to ground, this plate will be charged to negative voltage. I mean, it will be a negative charge on the other plate, and this plate will be at positive voltage. It will contain positive charge. Okay, so the direction of flow of current, positive charge is flowing in this direction, so it will be like this in one half cycle. So it's a non-inverting integrator. You will get the same transfer function, but it will be with a positive sign. So the advantage here in this integrator is realized using switched capacitor is that the time constant is independent of process. If both the capacitors vary similarly, then your time constant is going to remain constant. If you can build an integrator with a constant time constant, with a fixed time constant, and we also have a gain element which is independent of process, then you can realize any filters which will be process independent. The transfer functions will not change with process. That was the major advantage. But here I told one important point, that you need the clock frequency to be much higher than the input signal's frequency. And within this clock interval, because your clock frequency is very high, you want your op-amp's output to also to settle. It has to settle within a half cycle, right? Op-amp's output should suddenly charge to it should be able to deliver a charge within a very short interval, within t by 2 seconds. So the bandwidth necessary for the op-amp also increases significantly. That's why this doesn't find applications in very high bandwidth applications. If your signal, say video signals, will have very high bandwidth, so in very high bandwidth, high data rate, or very high bandwidth applications, you don't see them. Still, in they peaked. All the applications of switched capacitor circuits peaked in 1980s and 1990s. But after that, digital revolution was so huge that it completely dwarfed it. So now, in very low frequency applications, we see switched capacitor circuits. If the input signal is of a very low frequency, we can have some moderate frequency clocks, and op-amp will also have some moderate bandwidths and all of that. So in the next lecture, I'll probably discuss a series of post a series of lectures on the CMOS op-amp design. Now we have seen some of the major applications of op-amps. Okay, so we have seen. Okay, so one of you are asking what type of circuits will use high bandwidth. For high bandwidths, we'll use continuous time filters, conventional continuous time filters, filters built using RCs and all that. Now today we do a lot of digital trimming and calibrations, so even that variation of time constant can be addressed. Okay, so we'll come to that later. In the next lectures, I'll start discussing about the design of CMOS op amps. Now we have laid down foundations for you to understand what are the different places in which an op amp will be used. Okay, so now based on that, we'll see which architecture of op amp should one choose. The whole idea of op amp discussion, design of op amp discussion, is entirely about picking the right architecture of the op amp for right applications. Okay, I'll stop at this point. Thank you.